So, as I mentioned before, Andy Ta is out, which of all people to miss is it's a real shame. And everybody here is great, but I think his talk in a lot of ways is sort of a hub for what we're discussing here. But also probably of all talks, it's probably the one that could step in and actually cover reasonably well. Andy and I worked together. He was our technician at Mica. So he actually worked for me at Mica, running the digital fabrication studio. And he's now at Rice. But so he's been working a lot at this intersection of open source hardware, open source 3D printing, and tissue engineering. In the lab where he is now at Rice, that's run by Jordan Miller, who's been doing a lot of interesting work, again, at that intersection. So these guys here for Jordan's work. Okay. So first, what is bioprinting? We see a lot of things, there's kind of a lot of buzz around this, but I feel like probably a lot of us have mixed ideas of what this is. I guess everybody's here, so we probably have some sense. It's a new word, right? It's relatively new, at least. And what we're really looking at is this process of generating spatially controlled cell patterns using 3D printing technologies, where that function and the viability are preserved within that printed construct. And that's kind of the hard part. Like squirting some cells out, placing some cells where you want them is hard, but what's really hard is making sure that they stay alive and actually thrive and grow after that. So I think John outlined a lot of these topics, like why do we care about this? The vast majority of this research is in the biomedical field, which is for good reason, you know. Like those guys are doing important work. So it isn't necessarily the work that we're doing here at Bugs specifically. We're really drawing in a lot of these technologies. So we'll see this as a recurring theme for today. So you get your cell, we try to get this a specialized cell, get this coalesced into tissue. From there you can form that organ. That makes a complex system, and then we have an actual organism. So the big thing, as John alluded to, is this notion of vasculature. So this is a slab of cells here. We can see these glowing cells on the outside indicate cells that are alive, and then we can see in this slab all the internal cells are dead. If we can run just some simple vasculature through that slab, see we get a lot more live cells. So this is a common thing that you'll see throughout this. Bioprinting is really a means of generating vasculature. And this is something that 3D printing is really great at. Complex forms with internal structures. It's super hard to make that kind of stuff any other way. You can't CNC mill this, right? You can't cast this kind of object in any kind of sensible fashion. But for a printer, these kind of structures it's not necessarily any harder to print this thing than it is to print a solid cube that size. In some cases, it's a lot easier. And that's kind of like the buzz for 3D printing, is that there's no cost for complexity. Okay, so most folks kind of probably came to hear about 3D printing through this kind of popular means of the RepRap, if you're kind of nerdy like me, or if you just kind of came about maybe through more commercial experience of like the MakerBot and things like that, which are kind of basically a commodified version of the RepRap project. But it's important to know that this is 3D printing is much more than just this fused filament fabrication. There's a lot of different technologies that go into this. So one of the approaches that Jordan Miller took is really he got together with some people from the hacker community in Philly and devised this special extruder for the printer. I think he was actually eating dessert one day, and there's like some kind of fancy dessert with this sugary like decoration on top, and he's just like, "Oh, this is what I need to make a vascular system that I can dissolve and wash out." So he set about figuring out how to make this. So this is using a sugar glass that they can devise a recipe for, and it has to get that to a high temperature, and then print that structure. We have a video of this. So here it is printing. This is what he calls the Barracuda printer. So it's extruding this glass, and it's kind of fine filament. So it's actually quite similar to your FDM, fused deposition modeling, or your fused filament fabrication in a lot of ways, except for with printing a liquid structure like this is a little bit more difficult for a number of reasons. But they've engineered this material so it's quite plastic. So you can see right now it's going around just sort of printing some walls for what will sort of function as a vessel here. And then it uses this technique I like to refer to as blob and drool. So it's going to blob a bit of material down and then just sort of pull that across. So you get this really nice thin little fiber of the sugar glass, and then that stretching motion, it cools as well.
Is this sucrose? What's he using?
What's that?
Is this cane sugar?
I'm not sure exactly.
They call it carbohydrate glass.
Yeah, thank you.
Carbohydrate.
Yeah, I'm not sure. I think originally they were drawing on a lot of the kind of glass, the sugar glass recipes like used in Hollywood. Yes.
It's like table sugar.
I don't know if it's plain table sugar or not. I'm sorry. That's a yeah. I don't know. So that's structure there. Okay. So that we can see has a lot of similarities to that FDM. There's a number of other technologies for 3D printing as well. We have SLS, which is selective laser sintering. So that's a process where you have on one side of the chamber, you have this whole vat of loose powder of some sort. And then the other side, you have this build platform. You pull a very thin layer of that powder across onto your build platform. And then you use a laser to fuse those particles together. So that laser dances across that surface, fusing those patterns together. And what is a cross-section of your 3D model. Then that build platform lowers, another thin layer of powder comes across, laser hits that, fuses the next cross-section. So you've built your whole object up inside this vat of loose powder, and it's all fused together. SLA is a similar process in that it's also using a laser, but it's typically using a liquid resin that's UV curable. So here's a top-down style. So it's going to print that cross-section of your model, fuse that layer of resin, lower the platform down, and then print that next section over and over. That makes sense to everybody, these processes? Lastly, we have this inkjet technology, which typically is also using a UV curable resin. And you're going to print out your model in a liquid resin, hit that with the UV light, and it turns rigid. Where you have overhangs and things like that, it prints a support material that's somehow soluble. Okay. So we have some little sample video here. So this is a sample video of Andreas Bastian's open SLS project. So this is an open source SLS machine here, and in this case he's printing with wax. So Viper system's still looking a little crude at this point. See the laser come through and just fuse that wax together. So this is a machine that was developed at the Miller Lab, and they've used this a little bit with this testing with wax, but also using it with sugar and also PCL, polycaprolactam. So here's some prints done with SLS and nylon. That's a really common material for this, and it's a really great material for 3D printing. You get nice, flexible results. So this is some work from Nervous Systems. It's a really great design duo doing a lot of parametric modeling. Then over here we see the PCL centered from Andreas Bastian's work. So SLA, it's our stereolithography, and this is used in this video. Seeing this, this can be done a number of different ways. In this case, it's done with a DLP projection. This is sped up dramatically. Though there are some new technologies that have come out recently, referred to as this clip approach, that does allow that process to go a lot faster.
I noticed that SLA scene that you just showed does not show a scaffold. Does the looking method have scaffold?
Yeah.
I was surprised. I thought the power method was the only method that did not require scaffold.
It depends. So if you have, you know, say we've got a structure, well, we're looking at it upside down, it's printing like a, if you end up with parts that are just totally floating in space, that doesn't have anything that it's attached to, then those are you're gonna have issues
I
there.
am correct in saying that the powder method is its own scaffolding.
Yeah, which is the real benefit of these powder methods, whether that's using the sort of inkjet in powder or the SLS. Absolutely.
If you have a very complex structure and the process is putting scaffolding in and around that structure,
Yeah, even these, even the UV resin-based prints where you're using a support material, you know, a lot of times if you've got a really delicate object, it'll print beautifully, but you'll destroy it trying to clean it. So, thanks.
So whatever method is used for BioPrinting, considering the complexity, have to be non-scaffold requirement, which would disqualify 2 of those 3 methods.
Well, I mean, you can still do, like for instance, you can still do this complex structure with a lot of negative space in here with SLA. You know, here you see these points, depending on how this was printed, if you've got certain points that are just totally floating out in space, so like, you know, if I'm doing my fingertips and I start here, I can print them up, and that's great. But if I've got a fingertip with just kind of dots floating out in space, then there's nothing for it to attach to, and it's going to kind of wash away in that process. Does that make sense? So you can still do with SLA really complex open structures. That's possible.
You have the scaffold that just like it's a different insulator, like it's there, and then some sugar music.
That's the point of the glass method that they were talking about to build the vascular structures. Is they create the sugar space, they print the bio material around it, and then they wash the sugar out, and that leaves the vascular holes.
Yeah. So all these approaches, that scaffolding is something that's temporary. Sometimes that's used as a you know, in that case of the glass, you've got the sugar, and then you pour in a mix of hydrogel and cells, and that's going to set, and then you can wash the glass out of that. So then you've got your vascular system in this hydrogel sort of slab. So that's one approach. Other approaches, you'll just create a really loose, open structure that your cells can adhere to, and then you can sort of wash your media through that. But there's enough open surface, and then eventually your cells consume that material, or it just kind of evaporates over time. So that's the kind of thinking with a lot of this printing directly in hydrogel. So you can either you can either suspend your cells, you can create a structure and then add your cells onto it, or you can have your cells in the hydrogel and print negative spaces to function as vascular systems. Those two approaches kind of make sense to people. So there's we could probably divide bioprinting into two general categories. One where you're printing a scaffolding first and then inoculating that scaffold with cells, and the other where you're printing directly with the cells. So this vasculature, that's kind of the big challenge with all these things. Just keeping all those nutrients, keeping all the cells alive, etc. Okay. So this is Andy's email. You can just call him and harass. You can just email him right now and harass him a little bit. Questions?
So I guess the compounded field is that you don't want to build vasculature just per se, right? The idea is to frame vasculature so that you can fit some more complex tissue structure. So you have the focus compounds, so you just want to build vasculature, then you also want to build some complex tissue. You also want to build them together. How are they going to talk to each other? How are they going to emulate, all the tissue that you want to?
Yeah, so I think one thing that's important to understand when you're talking about printing a vasculature, it's a temporary vasculature. It's kind of a crude system that you can use to pump nutrients in, waste material out, until those cells can really build their own vascular system. Yeah. Typically.
I mean, what kind of anecdotal grail is, you can imagine, building the vasculature, seeing the tissue-specific cells around it, say, whether it's the pancreatic islets that are responsible for secreting insulin for diabetes, the liver cells, for replacing a liver, and you keep that alive in a petri dish, and so you can actually pump stuff on one side and stuff on the other, while keeping the cells alive. And then the idea is that you're able to pick up this and suture it to the blood vessels in a person, so their blood vessels can keep it going. And so once so first you have, I think you have to engineer the blood vessels first, right? And people are to keep all their cells alive, and then eventually, I think people are now starting to bring them together. So, but it's a big engineering problem. Again, it's this converging technologies, like building an iPhone, right? I mean, it's like you got GPS in there, you got screens, you got touch, you got all the software, bringing it all together, microchips. I mean, it's so powerful, and a long time for computer technology to get to this.
And then a consumer drops on the ground, and it shorts out.
Yeah.
But then the next one.
Right. So it's like iterative over time, right? And I would say we're in probably the third or fourth inning now of baseball games. So.
If I'm not mistaken, the first part, when they did the first part, they didn't even have the washouts then, right? And it still was booted up and started pumping for 2 or 3 days before the cells started dying off. Not the one they do, but
I don't know exactly what you're talking about.
That is to regenerative science. It's the first part that we've done that in the work.
Yeah, I don't know details there, but I mean, there's lots of things.
In terms of the scaffolding material, this kind of ties into John's presentation. I guess the whole point of a lot of the scaffolding is that it's biodegradable. It falls away over time. Are there any, biostructures where the growth period is over a period of time that's too much for, I guess, the structure that we have so far. Like the time scale is longer than.
The challenge tends to be actually getting your materials to degrade fast enough. In a lot of these cases, like the PCL and things like that. Correct me if you have any other information on that. But I think that tends to be the challenge. I know particularly with in some cases.
Yeah, it just depends on the tissue grade. So it's, some tissues you want to degrade way quickly, other times because then you want to balance the degradation with the replacement of the tissue. If it's bone, you probably need that structural component there a lot longer than you would for, say, liver, right? Which is load bearing. So yeah, I think the answer there is it depends, right? And so you'll see as people come up with new material systems, you can tailor in the degradation times, from days to weeks, months to years. But it's marrying it all up and then putting the dedication into making a specific tissue work. Right, it's one thing making a material system that has that capabilities. That discovery, there's still 95% of the work that needs to be done in turning into a new product.
Tom?
So I'm kind of wondering, it seems like that most of bioprinting, when we're talking about human cells, is taking place with differentiated cells. Cells are specialized for certain functions. So is there work going on with undifferentiated cells and getting them to differentiate in situ so you can, print the vascular network or whatever, and the liver or whatever, growth factors are necessary to differentiate into their specialized subcomponents, organs?
Yeah, but you probably can speak to that topic.
Yeah. I mean, it's for things like bone and cartilage, it's common to transplant undifferentiated mesenchymal stem cells, which is 30 million cells over time. It's for and there's all sorts of different strategies that are taken. I would say probably 20% or less are what you're describing right now for things like pancreas and the liver. But there's a clinical trial that just started last October, type of diabetes, pancreatic stem cells, and they are partially differentiated, and they differentiate the insulin secreting cells over time. While the vasculature transplanted into a thin sleeve, the vasculature grows up that sleeve, and then you provide the nutrients to those, as well as to carry the insulin away, so that the insulin can use the sugar away in the patient. There's a million ways to skin cat, right? And people are looking at all, but I would say that the majority of these are just still in early research in academic labs that are still 10 to 20 years from seeing the real application.
I know in some cases, like printing with when you're doing the bone growth, printing with PCL scaffolding, will actually grind up bone and put that in there to encourage the cells to differentiate in the way they want.
I'm wondering about resolution from the bioprinters, 3D printers in general, and what value different resolution machines have in tissue media.
Yeah.
Like a DIY, lower cost printer can do millimeter or hundreds of microns. A high-end printer can do 100 micron features with walls and holes. What's the value in the tissue engineering world of those different categories of resolution? And is there value in developing printers that can do micron?
Yeah, I think again we're really looking at the fluidic properties. So that getting the vascular system in there. If you can have a really nice diffuse vascular system, that's great. I think though
that resolution is on tens to hundreds of microns.
Right.
That's
Yeah. Yeah, blood vessel. I mean, the smallest microvasculatures still have 20, 30 micron ear diameters. Right? So, the larger blood vessels are limited.
Yeah. I think, to me, I mean, we tend to think of like these digital fabrication techniques as being like really precise. But I think in this instance, it's like the really crude tool. Like you can kind of like get the cells in roughly the right location. And the really amazing thing is the ability of these cells to know what they need to grow into and to know how they grow and to form those really complex structures on that much smaller scale.
What is the lumen size, the size, micron size of most of the material cells? Say you were using like flow cytometry as pushing in your channel for microfluidics as your intrusion.
Yeah, I mean, 130 microns probably. Size.
All right, I'm going to cut myself off here. So we have plenty of time for more questions and more conversations. That's kind of what the day is all about.